Welcome everyone. We're going to do section 6.1 today, which is use similar polygons. This is part of our chapter 6, which is on similarity. The big idea for this section is how proportions can be used to identify similar polygons, and also how to calculate what's called the scale factor of the sides. So below, I put some pictures to get you thinking about what does similarity actually mean? When are two things similar to each other? Does it have to do with color, size, shape? So we're going to take a look specifically at what does it take for polygons to be similar. So our definition is that polygons are considered similar polygons if all of the corresponding angles are congruent and the corresponding side lengths are proportional. Okay, so let's take a look at that a little bit closer. Below, there's two quadrilaterals, ABCD and EFGH. So right below those is a similarity statement. So we see ABCD is similar to EFGH. Okay, so that similar symbol there below, I'm just going to point that out a little bit more here. This symbol right here means is similar to. Okay, so it's close, as you noticed, to what we had for our congruent symbol, except there was an equal sign as part of that. So this one, we removed the equal sign, saying that, no, these are not the exact same shape, or sorry, the same figure, but they do have some things that are the same. So in this case, they have angles that are the same. All right, so if we look a little bit more closely, we know that all of the corresponding angles are congruent. So if I was to label those, let's use a different color here. We have angle A, which would be congruent to angle E. Angle B is congruent to angle F. Angle C is congruent to angle G. And angle D is congruent to angle H. And all of those can be identified either in the diagram or in the similarity statement. Okay, so now let's talk about this idea of the sides that are corresponding being proportional. So proportion is a ratio of the sides when we have equal ratios for each pair of sides. So if I look at my pairs of sides, I know that AB and EF are corresponding. So if I set those up in a ratio, I have AB over EF. Now that ratio is going to be equal to the ratios of all of the other corresponding sides. So what does that look like? Well, I'm going to set that equal to another ratio of corresponding sides, like BC and FG. Okay, so whatever the proportion is for one pair of sides, it's the same for every pair of sides. Okay, let me move this over just a little bit so we have some more room here. Ooh. All right, and then we're going to continue writing our ratios. So not only are these two equal, but they're also equal to the other two ratios of the sides. So CD, which is corresponding to side GH, and then side AD, which is corresponding to side EH. Okay, so I can take two of these at a time, or I consider all four at once, but I have a proportion showing that these ratios are all going to be identical. All right, so let's talk a little bit more about that idea of those equal proportions by looking at this example. So in the top, I can see that I have triangle RST is similar to triangle XYZ. And again, you want to see that statement. That's what's going to tell you you're now working with similar figures. So I have all the information given to me in the diagram. The first question is asking me to find the ratio of side RS to side XY. Okay, well, I'm going to set up that ratio first. RS over XY. So in the diagram, I have numbers associated with both of those sides. 25 over 15. The only thing I have to do in order to come up with my ratio now is to simplify this. So since both numbers can be divided by 5, my ratio is 5 to 3. So that's the ratio of side RS to side XY. Now, because these are similar triangles, that means all of the sides are going to be in this same ratio. So if I want to find the missing side lengths, what I'm going to do is use that 5/3 and set it equal to another ratio of sides where I'm looking for one. All right, so let me make some more room here. So I know that I'm going to use the 5/3. And now I'm going to find another pair of corresponding sides. So I have RT in the triangle on the left, which would be in a ratio to side XZ in the triangle on the right. Now I know what RT is. RT is a length of 20, but XZ is the one I don't know, but that's what I'm going to find. So because it has to be in the same ratio, I know that it's going to be equal to that 5/3. This is called my proportion. So now to solve it, there's a couple different ways you can actually go through it. The most convenient way is usually just to cross multiply. So that's what I'm going to do here. So I'm going to multiply 5 times XZ, side XZ, equals 3 times 20. Okay, so 5 times side XZ equals 60. And then I can divide both sides by 5 to come up with XZ equals 12. Okay, so I'm going to go write that up into my diagram. I found the length of side XZ. And it looks like I still need YZ, so I'm going to set up another proportion. Again, RS to XY was a 5:3 ratio, so that will be equal to the ratio of side ST to YZ. Okay, now I'm going to rewrite this. I know that ST has a length of 30. YZ is the one I'm looking for. Cross multiply. Okay, make a little bit more room. I get 5 times YZ equals 90. So I'm going to divide by 5 and come up with YZ equals 18. Okay, so now I'm going to go back up, put 18 into my diagram, and now I have both triangles with all 3 lengths in them. Okay, so now we're going to talk about this term called scale factor. So the definition is, if 2 polygons are similar, the ratio of the lengths of their corresponding sides is called the scale factor. Okay, in the previous example, when we found the ratio of those 2 sides, we came up with 5/3. So we would say that the scale factor of those 2 triangles was 5/3. Excuse me. Okay, so now let's take a look at the example below here. In the diagram, I have triangle DEF is similar to triangle MNP up here. Okay, so now I know that all of my sides are in proportion, and I'm going to use that to determine the scale factor. So what you need to do to determine the scale factor is to find 2 corresponding sides, which you know the lengths of. So for example, let me highlight this. I know side DE is 9 and MN is 12. So I'm going to use those, excuse me, I'm going to use those 2 sides to come up with the scale factor. Oh, sorry about that. Let me get that back up here. Okay, so taking a look, I'm going to set that ratio up. So DEF to MN is side DE to MN, which is 9 to 12, which gives me a scale factor of 3/4 when I simplify that. Okay, so now I'm going to look for the value of x. All right, I know I have my scale factor, 3 to 4, so I'm going to set up my ratio. So 3/4 equals x over 20, because side EF and NP, the long sides, are going to be in the same ratio, 3 to 4. So now I can cross multiply. 3 times 20 equals 4 times x. So 60 equals 4 times x. Divide by 4. And I get a value of 15. So x equals 15 gives me my one missing side length. Okay, let's keep moving. So this slide, I want you to pause the video for a second and copy it down, and then you can come back for the explanation. In the top key concept, what we're learning here is that all lengths in any similar polygons are going to be in that scale factor ratio. Okay, now we're talking about any lengths that you can draw. So for example, in a triangle, the altitudes are going to be in the same ratio of those two triangles if they're similar triangles. If you draw the mid-segment in any two triangles, they'll be in that same ratio. So as long as they're corresponding lengths, they will have to be in the same ratio for the scale factor. If you look below in the theorem, because all the lengths are going to be similar, that means the perimeters of these shapes will be similar as well. So in two polygons, if you have the perimeter of one polygon and you know the scale factor, you could determine the perimeter of the other polygon using the same proportion that you would just to find sides. Okay, last concept that we cover in this section is just a very basic one. Similarity and congruence are related. So any two figures that are congruent can also be called similar to each other. They just have a scale factor of 1. Okay, so in the diagram below here, if I look at those side lengths, if I set up my ratios, saying that these are similar triangles, I have side AB is to DE, as AC is to DF, and as BC is to EF. And if I look at all of these ratios, I have 5 over 5 equals 6 over 6, which equals 7 over 7, and all of those equal 1. So as soon as you see that, we're actually proving that these triangles are not just similar, but they're congruent. Okay, so you still can use the idea of similarity for congruent polygons. Okay, here's where I'm going to leave you. So here's an example where we have two polygons, A, B, C, D, E, which is similar to F, G, H, J, K. So we do have our similarity statement up here at the top. Okay, use what you've learned in this section and try questions A, B, and C. See if you can come up with the answers. And we'll start with this example in class the next time I see you. Okay, so go ahead and pause here if you want. And then make sure, bring all your notes and any questions you have on this material with you to the next class. See you then.